Hi everyone, so welcome to netgatechemistry. So today we are going to study the topic chemical bonding. Before I start the topic, I want to tell you guys that I'm going to upload all the possible videos, actually all the videos in which I'll be covering all the topics required for your net and gate exams, okay? So first of all, we are going to study about the shapes of orbitals. Shapes of orbitals. First, we have our s orbital, which is spherical in shape and very symmetric in nature. Okay, you can write it. It is spherical in shape and symmetric in nature. First, second is your p orbital, which is dumbbell in shape. Okay, third is your d orbital, which is double dumbbell in shape. Okay, so these are the shapes of the orbitals. So this was the basic necessary to tell you guys about a very important concept, that is penetration and shielding. Okay, before I start this important concept, I want to tell you guys that this chemical bonding chapter, it comes for 12 to 18 marks approximately in your net exams. Okay, so we'll start with penetration. Consider this is your nucleus. Okay, I'm taking 2s nodal plane here and 2p nodal plane here. Now you all can ask a question, why not 1s? Where is the 1s gone, right? So for that, I want to tell you that for penetration, we compare two orbitals, okay? Or if I want to take 1s orbital, then I'll also have to take 1p orbital, but 1p orbital does not exist. Okay, so I'm not showing 1s here. Okay, 1s will be somewhat here, right? So now see, we know the shape of s orbital is spherical and that of p orbital is dumbbell in shape, right? So what happens is, because s orbital is very symmetric, it is spherical in shape. So if I want to represent it, I can represent like this. This is your nucleus, okay? Initially it was your s orbital, and your s and p, both the orbitals having same energy. If they are having same energy, then they will be present like this. P is dumbbell in shape and this is your s orbital, which is spherical in shape. So what happens is, your s orbital, this s orbital is very symmetric in nature. So the nucleus attracts this electron density towards itself very strongly. So what happens, the 2s orbitals goes inside. See, this was initially your nucleus. This was the nodal plane for your 2s, and this was the nodal plane of your 2p. Okay, this was 2s and this was 2p. So now what happens? This 2s orbital, because this, it is very spherical in shape. Okay, very symmetric. So what happens? This nucleus attracts this orbital towards itself. So what happens? It goes inside like that. This is the new nodal plane. Okay, this is old nodal plane for 2s. This is new nodal plane for 2s. Okay, now what happens? This is your nucleus, positively charged, and this 2s has come closer to the nucleus. Okay, now what happens? This is the remaining space now. This remaining space is now occupied by 2p. That is, 2p has penetrated into the area of 2s. This is known as, this phenomenon, this is known as penetration. Okay, that is, this 2p has occupied, or it has penetrated into the area of this 2s orbital. This is known as your penetration. Okay, after penetration, what happens to 2p, that we're going to find out. See, this s orbital is now closer to the nucleus, so it is now going to shield the charge of nucleus. The positive charge of this nucleus will be shielded by this 2s orbital more. So what happens, 2p now does not feel that much of attraction from the nucleus. It is not going to feel that much of attraction from the nucleus, so it will not remain at this distance. Because it is not feeling that much of attraction, it will go somewhat here, somewhat here. This is the new nodal plane of your 2p. This is new nodal plane of 2p, and this was your old nodal plane of 2p. Okay, so I'll summarize once again. This was your nucleus, this is your 2s orbital, and this is your 2p nodal plane. Okay, this is your nucleus. S orbital is spherical in shape, p orbital is dumbbell in shape. So because s orbital is very spherical in nature, the nucleus attracts it towards itself very strongly. Okay, what happens, 2s comes very close to the nucleus and shields this charge of nucleus. Okay, so due to shielding, 2p is now not able to feel that much of attraction from the nucleus, so it goes away. This 2p goes away, and see, this has gone here. So this is called expansion of valence shell. That is, the valence shell has expanded. Okay, this phenomena is very important because due to the expansion of this valence shell, there is energy difference created between your 2s and 2p orbitals. Okay, so now 2s is because closer to the nucleus, so it has lesser energy as compared to the 2p. That is, initially they were degenerate, right? 2s is equals to 2p, but after the penetration of 2p into the area of 2s and shielding of s orbital, shielding by the s orbital, what has happened, the degeneracy, this degeneracy has been removed, and the energy of 2s is now lesser as compared to the energy of your 2p. Okay, so this is a complete phenomena of penetration and shielding. It is a very important phenomena. Okay, so what important conclusions we can draw from here? See, the conclusion is that we have two types of systems. Okay, one is monoelectronic, one is your monoelectronic system, and other is your polyelectronic system. Monoelectronic systems are those in which number of electrons in valence shell is equals to 1, and polyelectronic systems are those in which number of electrons in valence shell is 2 or more. Okay, so for monoelectronic systems, for example, your hydrogen, your helium positive, lithium 2 positive, beryllium 3 positive, etc., the energy of your ns, np, nd, they are all same. That is, they are degenerate. Why? Because here penetration and shielding has not happened. Because for penetration we need to have at least 2 electrons. Okay, at least 2 electrons, so that one goes inside and the other feels less attraction from the nucleus and goes outside. So there are energy differences between those. Okay, for polyelectronic systems, for example, your carbon, nitrogen, maybe boron also, the energy of your ns is less as compared to np, as compared to nd, and so on. Okay, that is the energy, now these energy of S, P and D, these are not degenerate, these are non-degenerate now. Okay, so this is a very important conclusion, that for monoelectronic systems the energy remains degenerate. Okay, now we are going to study about the, we have already studied about these shapes. Now we are going to study about the orientation. Okay, how these orbitals are oriented. First of all, we're going to study about the s orbital orientation, which is very easy actually. Suppose this is your x-axis, this is your y-axis, this is your z-axis. So s orbital is oriented like this. It is spherical in shape. S orbital is oriented like this. Okay, so maybe these are your axes. Okay, it is very symmetric. Next is your p orbital. For p orbital we have three types of orientations possible. One is your px, other is your py, other is your pz. How they are oriented? First of all, give the names to the axis. Okay, for px we have the orientation like this. The positive lobe will be along positive x direction. Py will be like this. Positive y lobe will be in positive y direction. For pz, positive lobe will be along positive z direction. These positive and negative are nothing but the phases. Okay, next is your d orbitals. Let's see first how many orbitals we can make for d, how many orientations are possible and how many actually exist. Okay, so for d orbitals, how many orientations we can make? We can actually make 6 orientations, believe it or not, 6 orientations. Okay, there are 6 orientations for your d orbitals. First of all, we'll make some simple ones: dxy, dz, dzx. First we'll make these three. For making the xy, dz and dzx, I think we need only x and y. For this we need only x and y, so I'll remove this one. Okay, for dxy, suppose this is your x-axis, this is your y-axis, dxy will be somewhat like this. Okay, for dyz also I don't need 3 x's, I'm okay with 2 x's. dyz will also be like this. Okay, for your dzx also I don't need 3 x's. Okay, dxy, dyz, dzx. For dx square minus y square, what can we do? See, if this is your x and this is your y, this can be your dx square minus y square. Other possibilities? Other possibilities are okay. You can make positive and negative loops. Okay. So To find out total number of d orbitals, we use the formula 2l plus 1. Because we have d orbital, so the L value is 2. So theoretically 5 orbitals are possible. So what would have happened? These two orbitals would have undergone mixing. How? See, this positive lobe would have undergone constructive interference. Okay. What happens if this is your z-axis for constructive interference? And if this is your x, this is your y. X and this is your y. Along x and y axis. This is along your x axis. This is along your y axis. So this is your x, this is your y, along x, along y. They would also have undergone mixing and they would have formed ring-like structure like this. Okay, this is your positive lobe, this is your positive lobe, positive lobe. Okay, so because this orbital has been formed by the mixing of these two orbitals, this orbital can be named as d of 2z square minus x square minus y square. Okay, because these two orbitals have undergone mixing and formed this orbital. These two have undergone constructive interference, and this x and y they have undergone mixing and formed this ring-like structure. Okay, to understand the interferences, I'll give you a small idea about constructive and destructive interferences. Okay, suppose we need a very tiny bit of knowledge about this actually. Suppose this is your psi positive, like this. This is your positive phase, negative. This is your positive phase. Okay, this psi positive undergoes mixing with your psi negative, like this. This is your psi negative, negative, positive, negative. It undergoes destructive interference. And if this one undergoes mixing with this, it undergoes, if these two mix together, it undergoes constructive interference. Okay, so what I have told you earlier, that we have these two orbitals like this. This is your z direction, this is your y, this is z, and this is your x. I'm making dz square minus y square and dz square minus x square. Okay, this is your positive lobe, this is your positive lobes. Okay, what I'm saying is that these two would have undergone constructive interference because we know the electron density which is present in an orbital, it is in the form of a wave functions. So wave functions, whenever superimposed on each other, they undergo constructive or destructive interferences. So these two positive lobes, positive on positive, will undergo constructive interference and form somewhat like this. See, somewhat like this. Okay, constructive lobe. And see, okay, this is your x direction, this is your y direction. If this is lobe along x-axis, suppose it goes up here. This is lobe along y-axis, suppose it goes up here. These two would have undergone mixing with each other and form a ring-like structure over here, which I have showed you earlier, it is a negative phase. Okay, so this is your d2z square minus x square minus y square, or roughly you can call it as dz square. So there are total 5 orbitals, 5 orbitals of dxy, dyz, dzx, dx square minus y square, and you can call dz square. Dz square is nothing but d2z square minus x square minus y square. Okay, so for this video, this much is enough. I think we'll continue the other topics in the next videos. Okay, make sure to subscribe if you feel that this content is important for you and it has helped you even a little bit. Please subscribe. Thank you.